Hello, I'm Dr. James Dborin, co-founder and head of research here at DoubleWord AI, and today we're continuing the Behind the Stack video series on self-hosting LLMs, looking at the topic, which quantization type should I choose? So if you're familiar at all with the open source self-hosted LLM landscape, you would have seen all sorts of quantization types come up at some point, whether you realize that that's what they were or not. You might have seen models described as appearing in GGUF format, AWQ, GPTQ, FP8, and all sorts of code names and data types that a model might be compressed to or quantized to. And in today's video, we're going to go through a broad way to categorize these types and which ones you should be looking into and using for your different use cases. So first, I'll quickly define what I mean by quantization. So quantization is broadly the process of adapting a model to use a smaller data type to decrease its footprint. So most models are distributed in 16-bit. This is usually FP16 or more commonly BF16 formats, and this means every parameter takes up 16 bits or uses 16 bits to describe it. So if I have an 8 billion parameter model, this means that in 16-bit format, the weights take up about 16 gigabytes of space. Now, they don't have to take up this much space. I can quantize them. You can take your 16-bit model, and there's all sorts of data types you can compress it to. You can compress it to one of various 8-bit formats. There are int8 and FP8 formats. There are more experimental FP6 formats. There are various 4-bit integer formats, bits and bytes, promotes, a normal float format. There are FP4 formats that are now hardware native on some of NVIDIA's latest GPUs at time of recording. There are all sorts of data types you can use. And there's a whole industry of research around how you can most accurately do this. Obviously, this isn't a lossless process. Going from 16 bits to a smaller bit width has an impact in accuracy, or like in the performance of the model. That's not what we're going to be talking about today. We're going to be talking about more like the considerations of assuming one of these popular formats is quite good at quantizing, which of these popular formats should you use? So there's broadly two ways to categorize one way that you could categorize the quantization, the available quantizations is into the following two categories. Category 1 is something I'm going to call this, the WX-A16 format. What this means is that the weights are stored using X bits, and I'll get into some examples in a second, but the computation or the activations are stored in 16-bit. So they're sort of standard format. One way you'll often see this described is weight-only quantization, insofar as only the weights are quantized. The other format that you might see is something that I'm going to broadly refer to as something like this. So in this case, the weights are stored using X bits, but the computation or the activations are also stored in X bits. So in this case, the computation is also compressed, and we'll look into the relative merits of these two approaches. So we'll start with WX-A16. So in the WX-A16 format, the weights of the model are quantized, but all computation that is performed in the model, all sort of temporary activations, all matrix multiplications, all of those things, are performed in the original 16-bit format. So one way to sort of visualize a matrix vector or matrix multiplication is something like this. I have some vector and I have some matrix, and it outputs, and you multiply them together to get some output. In this case, we have our matrix. So in this case, we have our vector, which might be stored in 4-bit, and our matrix. The vector will be stored in 16-bit. This will be the activation for the model, and our matrix will be stored in 4-bit. And you can't natively multiply a vector stored in 16 bits with a matrix stored in 4 bits. So at some point, this has to be converted to a 16-bit matrix in order for the computation to take place, and then for this to move on into the next part of the model. And there's 2 places this can happen. This can either happen outside of the matrix multiplication kernel, like here, in which case the matrices, the weights are converted back to 16-bit, and then they're put into some sort of vendor-supplied matrix multiplication kernel. Or, alternatively, if I duplicate this, it can happen within the kernel. So within the matrix multiplication, I turn the matrix into 16-bit and then multiply it by the vector. So this usually involves a custom kernel. So I can give some examples of quantization engines that do this. So for example, bitsandbytes, it will turn your weights into 16-bit and then use some sort of vendor-supplied matmul library like Kubla's in order to do the actual matrix multiplication. Another example of this, I think at least in the early days of the project, was ExLlama v2, does the same sort of thing. And then quantization engines that multiply, that do the expansion inside the kernel are, for example, AWQ, GPTQ, GemmLite, and a bunch of others. So what are the relative merits of the weight-only approach and these 2 sort of sub-approaches within it? So the weight-only approach is really good when your computation is memory bound. So especially during decoding, when a language model is generating tokens one at a time, the majority of the time isn't actually spent doing computations. It's moving weights between the GPU's memories, its VRAM, and its compute units. And this is the time that dominates during sort of decoding processes. So what weight-only quantizations have the possibility to do is decrease this quite substantially. So if you go from 16-bit to 4-bit, this becomes 4 times cheaper, and you can sort of theoretically see a 4 times improvement in your decoding speeds with these methods. But that's only true if you're using one of these weight-only quantization kernels or engines or libraries that does the transformation inside the kernel, does the upcast into a higher bit width inside the kernel, like something like AWQ or GemmLite. In these 2 cases, there's theoretically no speed up that can be achieved, and the only benefit is sort of having less space on the VRAM used up by the weight, so you could fit a larger KV cache, maybe your throughput could be a bit higher. But in general, these tend to be slower in all cases because they have the overhead of conversion that happens. Whereas these libraries here have a sort of theoretical limit of being about 4 times faster in the most memory-bound cases. Now, for a lot of these libraries, especially some of the earlier ones, in the compute bound mode, like during prefill, when you are taking more time doing compute, a lot of these libraries faltered and ended up being a lot slower than the sort of vendor supplied matrix multiplication kernels. So you would have a sort of graph like this. Be like, how compute bound are you? So when you're very compute bound, this is like when you're pre-filling. And then when you're not very compute bound, this is like when you're decoding. And something like AWQ, so this is speed relative to 16-bit. Something like AWQ would sit at like 4x. If this is 1x, so this is no speed up, it would look something like this, and it would become sort of significantly slower as you became more and more compute bound. And recently, more and more kernels are coming out that kind of look like this. So this is things like the Marlin kernels, which work for Ampere GPUs. I believe they're called the Machete kernels, which work for Blackwell. GemmLite, which are written in Triton, so they sort of can work on quite a few different GPU devices and AMD devices and things like that. And these look more like this. So they approach parity with 16-bit models at high compute bound loads, and then at decode bound loads, they're approximately 4 times faster. It kind of depends on the details, and that can be even higher. The theoretical limit of like 2-bit is 8 times faster. So it kind of depends all on the kernels and experimenting with that on your hardware, like how close you get to that theoretical limit. So this weight-only approach thrives here in the decode-bound world. So this is stuff like things with long responses, maybe agent models or reasoning models, things that like spend a long time decoding and generating tokens. That's where these sort of quantization, this particular weight-only quantization method is very useful. If you're in this compute-bound, prefill-heavy workloads, stuff like long document question answering, where you put in hundreds of pages and the answer is a single sentence, so you're going to spend more time pre-filling. They don't really do anything for you at all, other than reducing the space of the model on the GPU, giving you more tokens than the KV cache, so your throughput maybe get a bit higher and things like that. But even the perfect kernels here can't give you a speed up if you're using this weight-only quantization. So if you're in this scenario, where you're compute bound, you're actually more interested in using the other form of quantization. So the WX, activation X quantization. So in this form of quantization, once again, you have your matrix vector multiplication, and in this case, you're going to store both of them in some sort of compressed format rather than the 16-bit. They might both be int8, FP8, FP4, one of several other data types. That's the activation, and the weight is stored in a compressed format. And they have to be the same format. So in this case, you get a smaller footprint on the GPU, like you get a smaller footprint on the GPU. Your weights are stored in a compressed format, just like your activations, but also in this picture above, you are going to get a better performance here at the compute bound end. So if I redraw this diagram, it's going to look something like this. Again, you have some sort of decode bound workloads, prefill bound workloads. This is like the 16-bit performance, and in theory, it could look something like this. If you were doing sort of FP8 workloads, in theory, you might get 2x faster when you're very decode bound versus 16-bit because you're putting half the bits in. So before I said 4x because it was 4-bit. Now you're doing something like FP8, so it might be up to two times. But in principle, your sort of theoretical speed is like flat. So at decode heavy workloads, maybe it dips or something like that. decode heavy workloads, you might get this 2x improvement because you're pulling in 2x less memory. But at prefill heavy workloads as well, in principle, you're doing half as much work, or you're doing less work, and so it'll probably look something like this, and you'll end up above the 16-bit threshold, but maybe not exactly 2 times the 16-bit threshold. So it tends to be it can give you benefits at this prefill bound end, not just at the decode bound end. So if you're doing a prefill heavy workload, this is useful. So what are the sort of limitations of this approach? Well, for one, it tends to be less accurate. A lot of research has demonstrated that these activation quantizations are very lossy. They cause a lot of damage to the model. There's various reasons why. Sort of outliers in the activations are quite hard to quantize. There have been various approaches to try and fix this. I mean, the famous one is SmoothQuant, which attempts to make this process more accurate. And the other one is that it's very reliant on hardware features. So if you wanted to do like a 2-bit wait-only quantization kernel, you could write that kernel. You could write it using CUDA or Triton or Cutlass or any of these sorts of libraries. And if you were good at writing MATML kernels, you could get speed of light performance with that on any hardware that you really wanted to. But if you wanted to write like the same thing in wait, so you wanted to do like an FP2 wait and activation quantization scheme, you wouldn't just be able to do that just because you knew how to program with CUDA really well. You would have to rely on the existence of FP2 tensor cores, and those don't exist in any NVIDIA hardware or AMD hardware. And so in some ways you're limited by what the hardware offers. If the hardware offers FP8 kernels or tensor cores or matrix cores or whatever the hardware vendor calls them, then you can, or the vendor can, write an FP8 quantized MATML kernel, but if it doesn't, then you can't. So in some ways, this is restricted by hardware features. So for example, you can't do like an FP8 wait and activation quantization on Ampere GPUs like A100s, because there are no FP8 tensor cores on A100s. There's only int8 tensor cores. And so you're sort of fundamentally limited by that. And if you wanted to deploy this model on heterogeneous hardware, you would have to figure out how to do that. This one might need sort of SmoothQuant, but on Hopper and Blackwell GPUs, there are FP8 tensor cores, and lots of people have produced FP8 models to run on those. So they're a bit less portable than wait-only quantization models, as well as the fact they have these like challenges with accuracy. But if you get that working in principle and you have prefill heavy workloads, this can be a lot more effective than the wait-only quantizations. So today in this video, we've looked at 2 different types of quantization, 2 broad families, the wait-only and the activation quantization, looked at their relative pros and cons, when they're useful, when they're yet less useful, and what you probably have to do to get them running. Thank you for watching, and please leave any questions under the video.